Okay, my outstanding friends, I am going to have fun today. If you are into any kind of geology whatsoever, you know what feldspar is. This is all feldspar. All this brown looking stuff. And guess what's inside of the feldspar is basalt. There's a coating of feldspar on virtually everything. And then inside is what they call basalt. And I do deep chemistry, I mean deep. And I recognize something in my mud fossils because this is a goose, right? That's a goose. And why does it have feldspar outside of it? And its feathers and everything are feldspar. Well, I know why it has it, and it's because of collagen and because of the chemistry of the collagen and how it protects this from its environment. And that's why these fossilize in such a manner as this. And even the bones themselves turned into mud fossils. And this has been DNA certified as human. And this is some kind of a new species of, I call them no-toes because the toes are encapsulated in here. We're going to be seeing this in a microscope. And I'm going to show you, believe it or not, as incredible as it sounds, this is nothing more than leather. Look at here, genuine leather. We're going to look at this in a microscope versus this. And then I'm going to show you where the belt loops are here. You see these little fibers? Well, what's up with that? Why is it fuzzy looking? Well, we're going to find out uno momento. And my friend here, Caesar, is going to keep an eye on everything. And first of all, we're going to see what Caesar's truly made out of. Because he's feldspar, just like all the rest of these things. But why is he basalt inside? Why is that basalt? And everything else is feldspar. Whoop! How did all that happen? And the same thing here. Right, that's the tibia, the big bone that comes down, and that's the fibia that sits on the side. It broke off, and inside is basalts. And when I show you what the chemistry of basalts are and the chemistry of feldspar, it's going to blow your mind. And then I'm going to tell you about the chemistry that's in your body and why you die after 4 minutes without oxygen, or 6 or 8 minutes, right around there. 4 minutes your brain starts to go bad. 6 to 8 minutes is the case is closed. Now, so what should you do if you run into a situation where somebody has lost consciousness and you can tell they're not breathing, but it just happened? What you have to do is CPR. Now you do all that stuff and you blow air in and out of them. Now, here is a left human lung. All right, there's the heart, right there. That's where the heart sits, right underneath the left human lung. So you want to be on that guy and pushing on his left side of his chest, or her, or whoever it happens to be. And that's where you're going to get the most push against the heart, because the heart would sit right there. All right. Now, we're going to look at what fascia is in the human body, membranes, skin, leather, egg, even an egg. That's an egg. And it's all basalt inside, totally different than outside. And the reason for it, and the same thing with this bone, same thing. That's a bone. The reason for it is the collagens and the keratins and the kerogens that make up membranes. And they have in them saturated with aluminum. This blew my mind. This blew my mind. Because if these things are saturated with aluminum, I would think we have to be saturated with aluminum too. So I looked in to see how much aluminum is in the environment. And guess what? Now, when I talk about the surfaces, this is what I talk about is feldspar. Inside, they have layers of feldspar material. They call different names, plagioclases and anthracites and so forth. Now, when we get, for me, the surface only is what I'm talking about. That is what I call feldspar. Rock-forming aluminum, tectosilicate minerals. There's 100% aluminum. Look, anytime you see that Al, Al. And then you always see O8, oxygen, 8 oxygens on these things. Every single one of them. Aluminum, aluminum, O8, O8. Aluminum, 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 O8, O8, O8. These are all different types of what they consider to be feldspars. They're not feldspars, they're different types of body tissues that have fossilized and become replaced, substitute of the minerals, or the body tissue has been stabilized with all this oxygen. These oxygens and these aluminums and so forth. They apparently, while we're alive, the aluminum must be a transitional molecule that aids in what they call catalyst and enzymatic reactions, where molecules are breaking down, and they do it like so fast, it's absolutely incredible. So maybe that's what the aluminum is, but we're loaded with aluminum. 1/3 of the Earth crust is aluminum. Whoever knew that? I didn't know that. Now, don't forget, the only time you ever hear about aluminum in food is when it makes you sick. Well, this is back in 2011. They were talking about foods and aluminum content of different foods, and they're saying it's very low bioavailability. Well, maybe it doesn't react and attach in your body, but it works with catalysts. Because look, aluminum is the 3rd most abundant element in the Earth's crust. Therefore, a natural component of drinking water, foodstuff, a component of many manufactured materials. Aluminum apparently does not attach to other things, because it says oral intake would appear to be the most important source of aluminum, blah, blah, blah. But it says it's relatively low bioavailability. That means it doesn't interact in your body. They don't think. But apparently, it is extremely reactive to these different molecules that are down or atoms that are right down in this range. Because this is what transition metals do, is they move products back and forth between high concentrations of electrons and low concentrations of electrons. And they have deep orbitals that can accept and give and take of these different bits and pieces. And you have to understand electron flood theory, because there is nothing that isn't made of electrons. So hydrogen is not one big proton. Hell no. It's 1,850-ish electrons. That's why the center is a dipole still, because electrons are dipoles. Shown this a bazillion times. And this all supports everything I'm saying. And if this is biology, which it is, no question whatsoever, and it is saturated with aluminum after dead, it means the aluminum plays some specific role in the biology of all this stuff, because it all is very dense with aluminum and oxygen. The two of them are bound together now. 8 oxygens and aluminum in every single feldspar. That's pretty serious. Okay, so now I'm freaking out because I'm realizing everything is saturated with aluminum. So I figure, well, if it's not normally bioavailable, it has to be a catalyst. So listen to this. New tricks for an old dog. Well, I'm an old dog, and this is new to me too. Aluminum compounds as catalysts in reduction chemistry. What is reduction chemistry? It means when you eat something, it's big chunks of things, and you want to reduce it down to its individual components. And this is what aluminum compounds do as catalysts. This perspective discusses recent results on the application of aluminum compounds in catalytic reduction processes. And then they talk about some kind of technical stuff. But a growing number of well-defined molecular compounds, cationic and neutral, are also being used in this chemistry. And it is all due to this aluminum. Now check this out. Alright, we're going to talk about the catalysts right now. What is a catalyst? As I said, they can really increase the change in how something decays by factors that are just unbelievable. And the particle itself doesn't even get used. I'm going to give you an example, and this is true. In less than a fraction of 1 second, one single enzyme, which is a catalyst, can change a million other molecules in a fraction of a second. And guess how long it would take to do that if it was left alone? And it would do it, because it's a chemical breakdown. It would take years. So think of the factor, a quarter of a second versus years, and it didn't even use itself up. If there's a whole bunch of more of that stuff laying around, it's going to break down a whole another million in a quarter of a second, another million, and then when it has nothing to break down, it goes away. How cool is that? That's what an enzyme is. That's what a catalyst is. Now, they can make all kind of catalysts to break down all kinds of different particles and this and that and so forth for trying to make things for, industry. However, when you go to enzymes, it's a different story. Enzyme catalysts occur naturally. Natural enzymes. They're just where they come from. They come from bacteria. They don't occur just naturally. They come from bacteria. Well, yes, okay, I'm sorry. I should just shut up. Enzymes, catalysts that occur naturally in living organisms, but made by also living organisms living inside of that living organism. Almost all protein molecules, typical molecular masses of 20,000 to 100,000 AMU. Well, what's an AMU? It's an atomic mass unit. Well, what does that mean? Every atomic mass unit equals one proton. So they're talking 20,000 to 100,000 protons make up a protein molecule. Well, guess what they don't understand? It's every one of those atomic mass units is not one. So it's not 20 to 100,000. Multiply that number times 1,839. And that's how many electrons that has. So this is going to be bazillion-zillions. And that is what is doing all this transfer of molecules. Now, aluminum appears to be in a niche that it doesn't attach, but it's working through these very, very intricate processes of molecular change, atomic interactions, to stabilize something down to a reduced product, basically. And here's what they're talking about. Enzymes can increase reaction rates by enormous factors, up to 10 to the 17th power, faster than uncatalyzed rates, which I told you, it's insanely fast. And they tend to be extremely, very specific. They're targeting one specific thing to break it down into ammonia disulfide. I'm just throwing a thing out there. I don't even know if that exists. But let's just say that's what their job is. And that is from an enzyme. And where did an enzyme come from? As I said, they come from bacteria. And where do bacteria come from? They live in your membranes. They're what's called membrane-bound bacteria. If you don't have those, you're going to be sick. That's why I've been saying probiotics is your immune system, and these are the things that should be living in you. We don't know what is it where in you. There's so much diversity in your body, and every bit of your body has requirements for different chemistry. Your lymph system is your garbage dump. Your stomach is it breaks down with acids, and you have to absorb all that stuff through your intestines, and you have to stop it from being acidic in your small intestines, and your colon has to absorb all your other fluids back in, and this and that, and your body has to move all these things around. If you don't have oxygen for 4 minutes, your brain starts to die. At 8 minutes, it's all over. So we know that oxygen is playing an enormous function, and now we also know that every time you see oxygen in aluminum, it's in Feldspar. This is absolutely mind-blowing. This is absolutely over the top. I just learned about this hours ago, so I'm freaking out. I just didn't put it together until I started going deeper and deeper and deeper and getting into the enzymes and the catalysts and the feldspar and the aluminum and the oxygen. It's just way too much right this moment. All right, I got to be honest with you. I'm still a little freaked out after figuring out all this aluminum and oxygen and everything in. It's something to do with the catalysts and the enzymes are to do with the bacteria, and the bacteria is due to your immune system. It's membrane bound. Now, I am going to show you all the feldspar on the outside of this up here on the microscope, and I'm going to just go one after the other, and I'll say, this is the egg, this is the goose, this is the foot, this is the lung, and this here has both. This has the, you know, it has the membrane just falling off, basically. And then, of course, you got the bone and so forth. And I will just do them real quickly, one right after the other, because I need to do this in depth so you can fully understand. Now, this I made, many years ago, to try to prove my claims that this was all from the Great Flood. And all I did was I took fresh chicken and I put it in what I would consider to be the kind of fluids that would happen if all kind of creatures were all sort of in an ocean together. I never considered the possibility of boiling. Now, I had studied Velikovsky. For some reason, it just bounced off of me. And then I realized that I should have boiled this first, because that's exactly what Velikovsky said. It's written in all the ancient texts, literally all of them, that the oceans boiled. Now, if that was the case, these would get parboiled, and the membranes, just like you take right now, the bones and the tendons and all of that stuff separates. When you take it apart after it's been boiled, body parts, that's what happens. This is exactly what happened here. Now, the lungs, because at first I thought it's got to have something to do with the fascia, which is this coating. And I was going to call it fascia-facilitated fossilization, because look at it, it's the same damn thing. It's the same thing. And of course this was DNA tested. But see how flat it is? That means this was laying flat like this when it died. The goose, the same thing. The goose, and see the feathers and everything? It was laying flat like this when it died. This side's flat. Almost every one of them had a flat side. Now, like this one here, this is a lung, this halfway got its pleura on there, and then this inside of the lung with the pleura halfway pulled off, but still flat as a pancake on the back. You see, if I put water on this, you'll see this will be blood. This will be bloody, and this will be the fabric, which on this one is still coats the whole thing. You see this one here? That's the fabric. I'll put a little water on it in the microscope probably, but I don't think I'm going to do all this today. I'm just going to quickly go about 4 or 5 of them. But I want you to see my belt and show you that it's the same as all the rest of this stuff. It's nothing more than the fabric of life, which is collagens. And now I realize the aluminum must play a huge role, because this fascia, this coating, this feldspar, is saturated with aluminum once the creature's dead. Why? All right, this is the goose, and this is the feathers on its head, and this is the top part of the feathers on its head. You see all these little fibers and fabrics and these little black spots? That's what collagen is all about. Now, I'm going to go into his neck where the basalt is. This is inside of his neck. You see all the black stuff? That's the basalt and the chemistry of body tissue that's now stabilized. You see it? That's an artery or something. All right, now, right at the very edge, here's right at the edge, where right out there, you see, I'm going to wrap it around. That's the outside, which is the feldspar. And now look at that, you see that little line? It runs across between where the outside edge starts to meet up with this part right here. You see it? And then it works its way into the actual meaty part. So that's why they have all these different types of feldspar. But that's feldspar. They call that feldspar. Now that was the goose. Alright, so that's my buddy Caesar. Caesar Augustus. Now, I am going to do the Noto. Alright, this is so cool. I'm not going to do a whole bunch of them, but this is the Noto. Now, if I wet that, you'd see it'd be a little bit different, but not much. You see all those little black balls? In between those little black balls, there's all these little straps. And that's the Noto. Now, here's the bone. And this is the outside of the bone. See the fabric? See the little white fabrics all over there and the little black balls? The same thing. You see the little holes? Those are blood vessels. This is the bone, and that's the outside, which they would call a periosteum. Now, the inside of the bone down here is the marrow, where the marrow is, and all this black stuff inside the bone. See it? See the round circles here and there? Those are blood vessels normally. And outside of the bone, look at this. This is the only piece of bone left. Let me see if I can home in on it. That's as much of the bone as left. And it's almost visible and noticeable as bone right there. That little white spot right at the very, very tip to the right. I'm having a hard time catching it correctly. And look at, you can see the red. Let me see if I can home in on this. Oh, this is hard to do. Here we go. You see that little white spot right there? Basically in the middle. And then the little red blood vessels around it. See it? That's all that's left of the bone. And that was this bone here, this one. Now, yeah, that's enough for now. Well, here's the lung that was sent off for DNA testing. Now this one here is really dense pleura, absolutely dense. Now that's just outside all of the coating of the lung. Now down here is where I took the blood supply, I took the sample out to send off for DNA testing. It came out of these places, it was actually almost like raw blood. I'm not sure where it was, but it was down in this area somewhere. You know, and I drilled into it. I cut there. I don't know what that is. I don't think I did that. It's interesting, though. Huh. Looks like some kind of fracture line that was there by itself, because it continues up to the other side here. Interesting. Anyway, that's the lung. And what else do we have here? Oh, this is the one that has some of the pleura on, which is here. Here's the one, the lung that has the pleura still on it. Remember, it was all globbed up there. This is the pleura, which is the fascia. You see all the little strappy looking things and gooey looking. Now, I'm going to go down to where the lung itself is. And this is actually the lung. Although it does look very fibery. That's inside the lung. Interesting. This is the same piece. Now I'm going to move over to where the fascia is. And here's the fascia. All right, let's go back again one more time, because it's interesting. Huh. Basically the same. Well, anyway, enough of this. We're going to go deep, deep, deep into the chemistry. But I am just stunned at the fact that the aluminum is so ubiquitous in the environment, and we're told to stay away from it. Oh, it's no good for you. Well, it's a third of all the crust. That's what they say. I don't know if that's right or not. I had no idea if that it was that kind of enormous amount of impact in everything. It has to be. If it's a third of everything, it's crazy. Oh, I forgot to show you my belt. I am so sorry. Look up here. Wait till you see this. Remember I showed you all those little balls and straps? Check this out. This is my belt. I'm going to put this in the holder so we'll bring it right down. This is so cool. Now, this is the belt buckle hole right here. Let me turn this light on. Now, you see all those black balls? You see all the white fibers? The fibers attach to the black balls. And that is what allows your skin to return when it gets stretched and returns. Now, right around the hole, they show up as their fibers that are attached. They're still attached to the little black balls. So, this is what leather and skin and all of these stretchy fibers that are around lungs and organs and your skin, and all of that stuff has to stretch and come back, and that's how it does it. Excuse me, when you're alive, these can stretch and then they can come right back. That's their job. It's called interstitiation. I'll show you one last shot of that, and then if you're really interested, you've got to come back around. We need to really get deep into this, because as far as I'm concerned, so much is so wrong, and it needs to be addressed, because it relates to biology and chemistry and your health and everything, atomic physics, the whole 9 yards. So nothing here is correct right at the moment, and our history, and possibly even our eternity. I just don't know at this point. I just don't know.